Good afternoon, everyone. This afternoon, I'm going to give a talk about CBlock Posix compliant file system built on top of HDFS for Hadoop. And my name is Xiaoyu Yao, and I'm working in Hortonworks. I'm a committer and Hadoop PMC member. And my colleague, Anu engineer, he is also working on HDFS team of Hortonworks, and he is also a Apache Hadoop committer. So we have HDFS for supporting Hadoop workload for almost 10 years from the first day of Hadoop. And now, why do we need CBlocks? And what is CBlocks? CBlocks basically is a local volume created on top of HDFS backed clusters. And it can be mounted just normally as you use a local disk. And you can, once it's mounted, you can just format it just like a local file system with ext4 or XFS or any file system that is supported native on Linux box. And so the disks are basically persistent to a HDFS cluster. That means you can basically mount the disk dynamically when you need it, and you can dismount it and load it back later when you need the data for your jobs. And this allows some of the traditional non-HDFS aware programs to access basically like unlimited storage for your applications, where Docker. And there are a bunch of Data Lake 3.0 type applications, and they will be packed with Yarn plus Docker in the cloud environment. And this creates a lot of flexibilities with the CBlock, because it allows this kind of application to be deployed in the Hadoop cluster without even need to understand the semantics of the traditional Hadoop interface. They can basically use it just like a local disk. And many of the new applications, and they can still use HDFS, but the older ones can use this as a POSIX compliant file system to read, write, and create files on the CBlock backed storage. And it also allows you to persist the volumes, and these volumes will be backed by HDFS. And with the CBlocks plus Yarn and Docker, we are basically enabling a whole set of new applications so that these applications can run on the Hadoop cluster without even wearing HDFS at all, running on the backside. So CBlock is an effort made with a lot of contributions from the community. And it relies on a generic storage layer called storage container managers and the container layers. And we want to thank all the contributors to make this project possible. And Chen Liang and Muku from Hortonworks did a lot of work on CBlock. And right now, the CBlock is basically the first phase of the code is complete. And along with Chen and Muku, there are a lot of folks like Wei Wei, Yunbo, Yichin, and they are from IBM. And there are others, Nandu Kuma, Nicholas, including me and Anu. We are also contributing to the SCM, which support the container layer for the CBlock. And container layer was originally developed a year ago, and with Chris Norris and Arpit, and also Jitender from Hortonworks. And we need to special thank for Sebastian. He is the original author of JSCSI, which is a SCSI framework, so that you can implement a iSCSI server with a different kind of back storage. And without the support from CBlock, support from JSCSI team, and the CBlock won't exist. So we have a huge thanks to the JSCSI team and Sebastian. So this talk will take a very user-centric point of view and lead to the audience how the CBlock is used. And then we will go into some of the internals of CBlock, for example, the storage container layers and also the containers during the process of the CBlock volume creations. So we want to making sure we understand not only how to use it, but also the behind the scene how it works. And the CBlocks users usually start with just creating a simple CBlock volumes. Once the volume is created, it can be mounted just like a normal iSCSI volume. And we can format the volume just like we mentioned earlier with either ext4, XFS, and other file system, and then use the volume just like a normal local file system. So here is an example of how you can create, say, a 4 terabyte volume. And say if you have a user called Bilbo, and you can run the HDFS CBlock command. That's a new CLI command we introduced for the CBlock. And you can specify the username, the volume name, and the size of the volume. And then after that, you can run a bunch of standard iSCSI command, which basically will mount the CBlock volume as a local iSCSI target, and then use the second iSCSI admin command to connect to the local iSCSI target. And after that, you will have a local block device surfaced in your local Linux operating system. And then formatting and mounting is just like a normal volume. So the current state of this project is we're running the Hortonworks QE environment with CBlock server running. And this server is basically running as a log server. So we use it for saving the test logs. And the log server holds thousands of Hadoop regression test runs inside Hortonworks. And we have exposed the CBlocks volumes where NFS, rsync, and HTTP. And those are the 3 protocols that can be used to access the CBlock volumes. And we have many volumes deployed in parallel, and each of those are in a terabytes level of size, and they are being written daily with the regression test. And however, it is still in there are some work still in progress. For example, the Redis-based replication needs to complete so that we can finish highly redundant and support fault tolerance. Right now, it's a single copy for the blocks. And the CBlock volume size, right? We have already tested the volume size from one smaller, like 1 gig, to bigger one, like 60 terabytes. And we have more than hundreds of volumes used concurrently for the test environment. And it is a very stable and usable piece of software, and being used inside Hortonworks. And we also port changes from the Ozone branch, which contains all the daily update from storage container layer improvement continuously, and to ensure any new features introduced to improve the SCM also benefits the CBlock. So from this slides tells us the high-level CBlock architectures. We can see the piece here is most of the piece here running inside the data node. And the data node is basically a collection of containers. A container is just another abstraction layer on top of the existing HDFS storage locations. Just like today, it's running with the data node process. And each container contains a collection of blocks, and it serves the CBlock. It is managed by the storage container manager. The storage container manager is a generic storage layer that manages the whole life cycle of those containers, and it allows the SCM client to request create container, delete container, and get information or list of information about the containers of the clusters. And the CBlock feature is relying on the SCM to manage the containers. And on top of it, CBlock maintain a linear block address space so that it is mapped to the SCM container layer. On the data node side, we also have a CBlock iSCSI server. It is built on top of the JSCSI project so that it is talk to the both SCM and the CBlock server. So when the CBlock iSCSI server starts, it first talks to the CBlock server to get the address information and the container information. And once that is determined, we will directly talk to the SCM to access the corresponding block information based on the map from the CBlock block space to the SCM container space. Yeah, so this page basically already been covered when I go through the architecture diagram. And the one thing to note is the CBlock server. It basically maps the volume just like we showed earlier. When we create a volume, it basically maps the volume to a set of containers depending on the size. So we have fixed size of the container, so that if you say create 1 terabyte, and then it will map to 200 container, giving the container size, default container size of 5 GB each. And then the blocks, the mapping of the block to the container will be very simple and straightforward. There is no actual lookup on the CBlock server side once the I/O is invoked. So here is a simple workflow for creating a volume on the CBlock server. So, so what's happening here is the JSCSI server, the CBlock CLI basically talk to the CBlock server and to allocate the containers to allocate the containers, and then the CBlock server uses a fixed size for the container, given the block size provided by the command. And the containers then assume like a 5 GB each, and the block size also fixed, and a default to be 4 KB, but you can specify that when you create the volume. And when you're mapping the disk blocks to the container space, it is going to be straight like block 0 to 1,250,000 will be mapped to container 1 because of the fixed size of the container size and the block size. So the CBlock server maintains the volume name and also the container list, and that's all the metadata information that is needed. And when the client need to mount the volume and the information requested is also very clear and simple. There's no other consistent issue regarding the metadata side. So on the iSCSI server side, as we shown earlier, this iSCSI server side, the list of replicas for the client when it's trying to access the mounted disk, the block space is already known by retrieving the list from the CBlock servers. So this is a typical I/O path. We talk about the metadata in the early states, and here we talk about the I/O path. When the file system sends the I/O command to a mounted iSCSI disk, it first goes through the Linux kernel iSCSI disk driver. Then this I/O request translated into the block device accesses, and just a simple math by dividing the block address with the block size and the container size to determine which container it needs to access. And then the JSCSI server will directly read and write to the container using the container protocol without even need to contact either CBlock server and the SCM. So the I/O path is pretty much at the network speed. There is no actual metadata lookup during the whole process. And to speed up, we were aware of those. There are some costs associated with the replicated I/Os, and it can be expensive for certain type of applications. So we also provide I/O cache, a local I/O cache, to save the replication of the write operations. And so the write will directly reach the local cache if once the cache is enabled. And then the cache will be replicated on the background with asynchronous thread, and we will have faster write performance, and given a trade-off of some of the consistency because there may be read requests toward that. For some of those workload, we can either disable the cache, or we intend to support some read-through cache in the future. And during the process of building CBlock, we were relying on a common container framework. This framework was originally from some of the ideas that was discussed in the community to have a separate block layer, and we evolved the idea by having a more generic block service so that you can build I/O services with different storage format and the naming scheme. And we envision with this generic storage layer, we don't want any single point of failures. We want to have actually support for the generic block space servers, and also want to avoid the bottleneck so that we don't maintain. We will minimize the central state, and we don't want to have very fine-grained block reports that can potentially overload the central server, like the SCM server in this case. So from this is the high-level framework, container framework we are building. So this storage container layer, as we can see here, it is building with HA support. So we can have multiple storage containers, and we will have failover support, just like the HDFS HA. And then on top of that, we will have, on each of the data node, we will have a certain number of containers, which is a collection of blocks, and which are the replicated state machines built on top of Apache Redis project. And this framework, we will have different kind of services that will help build other higher level services. And the first service, which is the basic of all the others, is a replicated state machine. And the replicated state machine, we call it replicated log, and we use it to build the replicated block, container, and map services. So the replicated block is basically a key-value pair, and it's simply like assume you have a unique key, and each key and its value will be replicated. And then the replicated container is another abstraction layer on top of the replicated blocks. It's a collection of replicated blocks, and they will be replicated when it is opened, and so we have the notion of the opens and a closed container, and my colleague Anu will go into more details about this replicated containers. And also the replicated map is another, you can think of this as a distributed hash map built on top of this replicated log, and so that you can build name services easily, like a CBlock server and Ozone and the KSM that is used by Ozone today. And given this infrastructure, for example, we can build, in this diagram, you can see the storage container manager is a central piece that providing the service for replicate logs, blocks, and replicate containers. And on top of that, we can have CBlock server. As we discussed today, it's exposed linear block space for accessing with local volumes. We can also build KSM, which which we just recently finished most of the work on the KSM side to expose the generic storage layer to Ozone client. And we also plan to work on the name node side so that we can have name node talk to the generic storage container layer and to take advantage of this generic layer with minimal performance bottleneck, and the HDFS client will act as it is today to directly talk to name node without knowing the backend is switched to the storage container layer. Now I'm going to switch to my colleague Anu to talk about the storage container manager.
Thank you, Shayu. I'm going to talk about the storage container manager because that is the heart of what we are building. Really, this is a CBlocks talk, but it's a disguised talk for Ozone. Okay, so we've been working on this project called Ozone for 2-3 years now. And what it does is that it really tries to build, it started off as, hey, let us build an object store, okay? Then when we started working on it, what we realized was that, see, there are things in HDFS which are useful for building any distributed storage system. So then we decided, okay, maybe the right approach is to actually take these things out, which are generic, and build a framework so that anybody can go and build their own storage systems. And today what happens is that somebody invents a new storage system, and then they will say, okay, we need a cluster. They can't share HDFS because HDFS is production. So we want to get to a point where you as a developer can take this framework, build new services, and deploy along with HDFS. CBlock is one of those instances where we very rapidly, Jitendra came up with this idea and said, hey, can you build this? And we very rapidly built it and kind of productionized it. Okay? So Ozone is the same thing where it shares these basic tenants and builds it up. But it's all possible because of an old paper written by a couple of people from Yahoo. It is an HDFS Jira called 5477, where they said, hey, why don't we take the block storage out of HDFS and make it an independent thing? We said, oh, great idea. But block storage is not enough to build other storage systems. So we said, hey, you need to replicate the metadata. Oh, okay, that means that you need a Paxos or a Raft cluster. So Apache Ratis was born. So we have brought all this together and built CBlock and Ozone. And this is the centerpiece or the block storage for Ozone, for CBlock, and hopefully we are thinking that one day for HDFS or any other storage service you want to build. Okay? So what is a container? In HDFS world, when we started working, we found there are two things which block scalability. The number of name node entries, which are always in memory in name node, and the number of blocks. So there was this old idea called a super block. How do you take a lot of blocks and put them together? I was in a talk a little while ago, and they said, oh, erasure coding, you have to make really big files to put them together, and the onus is on you. If you're going to use it, make sure that your files are big. With containers, we are saying, don't worry about it. You write it any way you want it. It is our job to make it into big chunks. You don't have to even know about it. So that is it. A container is basically a collection of blocks which we bring together and create these huge blocks of 5 gig each. Why 5 gig? Because we said, replication is required. And in order to replicate in a reasonable time frame, we had to pick a sweet spot. So that's why we picked 5 gig, because we assumed everybody is going to have a 1 gig network. Okay? Each container by itself is a small key value store. Okay? So you can put a key and you can put a value out of that. That is how CBlock actually does its magic. You go to container 0 and you want to write block 0, you put actually a key called block 0 and its data. See, it's pretty simple. So now you can build anything on top of a container. That is at least where we want to get to. Okay? So essentially the value that you store inside a container can be an Ozone key value pair, an HDFS block ID and its contents, or a CBlock block, a real disk block thing. Okay? So each container has its own metadata, and that metadata consistency is maintained by Raft protocol. And we use RocksDB and LevelDB primarily to write out the data to the local store. And we also create something called a chunk. So let me go to the next slide so that you can understand how it looks like. So this is how a container looks like on the data node. See, earlier we used to have blocks and no metadata. With a container, what happens is that we have a container DB, the rocks DB, and then we have actual data streams lying around called the chunks. But inside the rocks DB, there is an entry, and it says, OK, for this key, here is how you will create those chunks. So we can bring in many, many files and treat it as a super block. So one of the things that this gives is that it gives us tremendous flexibility in deciding inside the container level how a thing must be stored. Because all we have is a contract. You have a key and you have a stream. But we get tremendous flexibility on how to actually store that block. I mean, there is no fixed block layout, or we are hoping that we don't get trapped into that so that people make assumptions about how things are laid out. So this is the data node side of a block interface. Okay? Now, storage container manager, as I said, is a block service, which we hope will become basis for you to build other storage systems. So these are the services offered by SCM. SCM offers a traditional HDFS block interface. So you can just go in and say, give me a block here. I want to write a file. I want to write 10 blocks. Give me 10 blocks of 256 MB each. Boom. It will give you 10 container locations to go write your block. There is actual container API. Like, for example, when we did CBlock, we said we don't want the name node to know what the blocks are. It will just kill it, right? Because one volume, 6 terabyte volume at 4 KB, creates so many volume and blocks, it is impossible for one server to hold it in memory. So we said, the CBlock can do a mathematical algorithm to find the location of the containers. All when you mount a volume is you get the name of 200 containers which make that volume, and then the client can actually manipulate it directly. So we have an API to work directly against containers. We have pipelines. Pipelines is, see, in the earlier world, you never knew about how to create a replication pipeline. Unfortunately, it also created a lot of issues. I mean, I can see some committers here, and they know that debugging the replication code is one of the hardest parts of HDFS. Okay? What we are saying is that, look, we give you one pipeline, and we want you to be able to create new pipelines for yourself. So there is a pipeline API where you can go create a pipeline. Today, we support a raft-based replication pipeline. And then there's a notion of pools. A pool is nothing but a replication domain. In traditional HDFS, if you have a 3,000 node cluster, a block can be replicated to any machine. With this, we are saying, no, what you do is that you define a pool. So you take 24 machines by default and say that's a pool. Okay? A block is guaranteed, that's a replication domain. A block is guaranteed to be in one of those 24 blocks, 24 machines. It gives you two advantages. One is that if 3 machines or more is lost, and I'm an HDFS guy and I want to really say this nicely, if more than 3 machines is lost, and if you have a large cluster, at some point you have lost at least one block. The reason being that every time you write a block, you're writing to 3 machines. And there are so many of those graphs inside your cluster. So if you lost 3, you lost 3 copies of one unique block. So it can cause data loss. But once you create these pools, you can now lose many, many, many nodes. Because if you don't lose more than 2 machines in one pool, you're safe. So you can actually, let's say you have 10 pools. You can lose 20 machines, and you will not have data loss. So this was work done by Facebook, and then later came out as a paper and 2 years ago as copy sets. So we took that idea and implemented pools. And another great advantage we get out of pools is the fact that we can scale linearly now. See, earlier, I see a Yahoo guy there, a couple of Yahoo guys, and they will say, oh, 3,000 machines, probably that's what you can scale with a single name node. And with this approach, we don't really have a limit because we don't process block reports for the whole cluster. We process block reports for 24 machines at a time and walk through a window of pools. So we can scale now pretty much linearly. The size of the cluster is not a problem. Okay? And then it also manages data nodes. So I'm going to take you through, I know it's a lot of information, but this is the block storage level for HDFS. So it is kind of dense. So forgive me for that. So SCM acts as a traditional block manager for HDFS, and this I just spoke about. It supports a bunch of APIs which manages blocks. Okay? the block API, I must call this out. Our design points, at least for the first release of Ozone, which we think will probably happen by end of the summer, we want to get to, say, 10 billion blocks. Okay? Traditionally, you talk about millions of blocks in HDFS, but we always want to say, OK, we want to get into the billion range and get there. But the block service just doesn't scale, because something like CBlock easily creates 10 billion blocks. So because of that, we also have another layer called the container services, where you can go in and treat your namespace as these huge chunks of data. You can say, I want 205 gig chunks. Let me manage it directly. We are hoping that other services will be written on top of it, just like CBlock, which can take care of the namespace explosion by keeping it internally and managing it. Okay, so one important thing, and I'm going to go this into greater detail, a major break that we made an assumption with HDFS is the fact that we've introduced a notion called a closed container. So a container can be open or closed. Okay? An open container allows you to read, write data, delete a key, and stuff like that. A closed container is immutable. Okay? So this actually plays into what HDFS has done for 3.0, which is erasure coding, where you have large chunks, right? Containers are now 5 gigs. You can erasure code. You don't have to really worry about it once this is in, because you don't have to worry about the size of your files, what is the erasure code policy, and stuff like that. Something that we should be able to take care at a much more internal level. But another main advantage that a closed container gives you is that now we can cache them, because a closed container, it's a full key value pair, but we know it is immutable. Therefore, you can cache it. Okay? So if Spark wants to cache it, it knows that this container is never going to change. So caching becomes a simpler problem because there are no updates. Okay? So in scale, it is very important. For performance and for scale, it is very important. However, it does come with its own catch. You have to delete a key. Somebody wants to delete a file. How are you going to recover this space? So in order to do that, we have to basically rewrite this container. So we remember that you have deleted a key, and then keep it around, and then eventually go and rewrite that container once certain policies are met. Okay? Again, let me go back to this. I just want to drill this in. You can actually have a container. It's not a traditional HDFS block. There are blocks which you can never modify in your life. Only thing you can delete to them is delete them. That's an immutable closed container. Open container is always replicated via Apache Ratis. They actually run Raft all the time, so you can write data and metadata, and they're guaranteed to be consistent. Whereas a closed container is replicated via SCM using pools. There are 24 machines, and we go in, and it's slightly different from the actual HDFS way, where data nodes decide when to send in a block report and try to kill, let's see, a name node. Instead, what we do is that we actually send a message to data node, those 24 of them, saying, send me a block report, because then I can process. So we can also control how many pools are processed in parallel. It's again for the scale reasons. Okay? So pipelines. What are pipelines? As I said, pipelines represent a replication methodology. I mean, today we have supported Apache Ratis. Tomorrow you might decide to do some other, maybe the classical HDFS replication strategy. But a pipeline just simply tells us, OK, this is how you're going to make the copy. A pipeline would be a way in which we would actually implement erasure coding. Right? So it just means some way to make sure that the replication happens, or the data is guaranteed to be consistent at this point. So this is the current implementation we have. And pools, I've already talked extensively about the pool. Basically, I just want to acknowledge Facebook's work and the copy sets paper. Only closed containers are replicated in a pool. So if I had time, I would dig down into how an open container actually transitions to a closed container. It's a very interesting algorithm. Yesterday evening, I had a 2-hour conversation with one of my colleagues. But a closed container actually is replicated just like a block. It can be under-replicated or over-replicated, and the SCM will decide how to replicate it, but only within that domain of a single pool. Okay? It also manages data nodes. At the end of the day, that is what we do. We have to manage data nodes. We make sure they get heartbeats. And we have pretty much borrowed very similar algorithms from the data node, name node world. The only difference being that we are hoping that some of the algorithms that we have used will make sure that your cluster is balanced most of the time. So traditionally, if you run a large cluster, you run a balancer all the time. This time, SCM actually looks at how the allocation, and I'll talk about the algorithms if you're interested. Walk over to me, I'll give you a great brain dump on how we actually do that. There are a lot of interesting algorithms gone into all these little dots there. Essentially, we make sure that our cluster is balanced most of the time. Now, just trust me on this. Okay? How do we deal with the loss of a single node? So Raft is a replicated state machine. They actually heartbeat all the time. So if you have a 3-node cluster, right, they are heartbeating all the time. And if there is one node went down, then you can talk to SCM, or the SCM eventually learns about it, and SCM will give you spare nodes. Now, what does it tell you? It tells you that all the nodes are not participating completely all the time in Raft replication. There are free nodes which are used only by SCM in terms of replication. So there are nodes which you can take write loads, and you can configure your cluster in any way. Suppose you have a very high write throughput load, you might want to have more Ratus lines. If you don't have enough of them, you can turn it down and keep a lot of data around. So that is one of the things that we have built. Okay? So loss of 2 nodes. Now, using HDFS does one thing very beautifully. You can lose 2 nodes, and HDFS will still stay up. You can deploy a cluster with 1 node. I don't advise it, but it's possible. You can write to a 1 node. Again, not a great idea, but still possible. With this, that's not possible. That flexibility goes away because replicated state machines cannot operate unless you have at least 2 out of 3. A quorum is met. One of the downsides with this approach is that when 2 nodes are gone, we can't even close down that pipeline. I mean, SCM won't send I/O to it because they will all fail. It will go to other, because there are many, many replication lines like this inside the cluster, so that's not a problem. But you can still read the data because there is 1 node standing. But we have no way of guaranteeing to you that that block is the latest you are seeing, or the data that you're reading is consistent, because it could really be a partition, because there are 2 other nodes taking the I/O somewhere, this node in a separated way, and you are accessing this. So this can create a problem, and we did a lot of simulation study. We know that the probability of a loss of a Raft ring goes down dramatically after you have a cluster of 17 nodes. Talk to me offline if you want to get more data on that. But so we need to tackle this problem. And this is not completely solved, and we're still working on it. So SCM actively tries not to get into this situation. One of the things it does is that if it finds a pipeline which is 1 single node is lost, SCM decides that, oh, I still have quorum, but let me move over to other nodes or other healthier Raft pipelines, which are fully 3. Until the 3rd one comes back, I don't have to really send I/O to it. So it just manages it that way. And another way is that we, at some point, go in and support multi-version concurrency control, so that, let's say you have a view of a single node, and you start reading from it, because that is what we know at that point. When these 2 nodes come back, and if they ever come back, and if they have a later version of the data, we are at least able to tell you that, hey, this is the later version of the data. It is very similar to writing a version number to our current pipeline. And then we can write checkpoints, which is that whenever you're doing I/O, at some point do an I/O checkpoint, so that you know, OK, up till this point, I know it has been replicated and I'm consistent, because I got the quorum, I was part of this quorum, and that data works. So these are the approaches that we are trying to work through and get it. So let me now do some marketing speak for me. So let's talk about the scale. I mean, this is the best marketing slide that I have. Okay? It is truly designed to handle trillions of objects. We can discuss how, again, offline. Okay? Pure marketing thing, container reports and heartbeats. I mean, if you worked with HDFS, okay, I'm talking to you directly. Okay, container reports and heartbeats are controlled by SCM. Since replication reconciliation is done pool by pool, SCM scales to very large clusters. Okay? Average size of the container is completely independent of the individual file sizes. See, no small file problem. You go write files the way you like it. You want to write 5 bytes? Welcome to my world. Absolutely not a problem. Okay? Ratis offers a fairly fast replication performance and maintain pretty high throughputs. Okay? And SCM assumes the presence of SSDs. So I remember reading a paper somewhere where somebody wrote this amazing paper saying, oh, SSDs make no difference for Hadoop. Not anymore. We welcome SSDs. We have also reached the world of modern SSDs today. Okay? And we support partial namespace. It was a work done by one of my former colleagues, Howie, and what it did was that it kept namespaces, some of it in disk and some of it in memory. So when you reach really large scales like 10 billion, 20 billion, it is not necessary that we have to keep the whole namespace in memory. We now have the flexibility to keep some of it on the disk. And that's why we assume SSDs, because IOPS matter at that point. Okay? And GC is not an issue because we allocate large parts of the metadata off heap. So for example, we allocate 30 gig of RAM and keep it around without GC pressure. Okay? So this one thing takes a lot of your tuning skills, which you have acquired over large time of running name-node away from you. But that is what SCM is. So see, my marketing slide is pretty good. I know that. Okay? So high availability for so there is a bunch of things that I consider sometimes that name-node makes name-node very complicated because of different versions of name-node. I mean, I heard Andrew speak a little while ago about how we can have now multiple name nodes, and then there is 2 name node architecture of HA, and then there is single name node. We don't want to make that mistake. We want to go out and say SCM is always HA. It is always replicated 3 nodes, always replicated via Ratis. KSM is always replicated via Ratis. CBlock server is always replicated via Ratis. In fact, HA is table stakes. We bring it always there. So that is what I want to do. I mean, Ozone, as I said, has been in works for a while. And a lot of people have contributed. I'm just not going to read out all the names. But a lot of people have talked to us. We have learned from a lot of earlier work. We have learned from every contribution in HDFS. So it has been a fantastic experience. And I do have a little bit of time to take questions now. Okay? Sure, go ahead. Oh, I mean, yeah, go ahead. I'll just repeat your question. Go ahead.
So, how do you handle partitioning namespace across different SCM instances?
When we have so there are two parts of the question. The question was that how do you handle partition across SCM instances? When we build SCM, what we do is that we run 3 instances of SCM, and that is replicated. All the information that we write, see in one of the slides, Jayu talked about a distributed map. We write to a distributed map, and that replicates over a Raft protocol. So Raft protocol automatically will elect a leader. So we just rely on Raft protocol. And the work has been done by my colleagues, especially Nicolas and Jing. He's giving a talk tomorrow. So the Raft protocol just helps us to choose the right thing. Now, there is another talk that we've been having where you can have many, many block layers. See, HDFS Federation, which is a great idea, used by a lot of people, especially Twitter, partitions a namespace into many pieces. Okay? But then people come across and say, oh, how do I do this rename across them? But in the block layer, there is no such problem. So literally, you could actually set up many, many SCMs and have one KSM or one name node work against it. Okay? But we have not reached there, so I'm just talking to you about my wish, where we get there. But SCM technically can do that, and then there might be one huge part of the cluster not available because those blocks are not available. But we have not reached there, so that is not a problem. But right now, this is how we handle it. Okay? Yeah, go ahead. I'm going to say something, but you cannot hold me to that, because date questions are very hard to answer, okay? I am going to say that we are going to ask, this is in a branch called HDFS 7240. We are hopeful that we are going to send out a merge by end of summer. We are very close. I have a running Ozone cluster in my labs today, okay? So I'm kind of very proud that, I've been working for 3 years. Nobody knew who I was. So, kind of gotten it done. So I can see the light at the end of the tunnel, if that is what you're asking me. So probably end of this summer, and that is one of the reasons why I said this is actually an Ozone talk disguised as a CBlock talk. So yes, you will see 2-3 months a merge request. Please +1 it. Thank you. Yep.
You have one SCM, or I should say one SCM, but one raftering or whatever per pool? Is that?
We do not have one raftering per pool. What we do is that we create one SCM, and the SCM basically, let's say we have 2,400 machines in the cluster. That means we have 100 pools. What we do is that we go in and start processing them one by one, and we maintain a heap of last processed pool. So it basically goes, say, pool 1, pool 2, pool 3. Maybe we'll run 10 of them in parallel, and they will have a last process stamp, so they move down to the heap. Then the next 10 is processed. In fact, there are a lot of interesting algorithms there, and I would love to go over in great detail with you, because it's pretty exciting. But so that's how we do this pool management. But let's talk offline if you're interested in how exactly we do pool management.
Okay, thank you, gentlemen. We're
Oh,
going
I'm
to
out
take a
of
short
time.
break.
Hey guys,
And we're gonna
thank you very much. It was very nice talking to all of you.
Excellent. We're going to take a short break and then get ready for our next session.